Hello, and thanks for using TickBoom. I've had a student send through this question, which is at first glance a roots of unity question, because we've got that classic z to the n equals 1. But what we'll see as we work through is that actually this question is guiding us step by step into an application of roots of unity results that lets us prove the area of an n-sided polygon, which is a very interesting way to go about it, and it's in the end quite a nice proof. But in terms of what the student has asked help with, this question has parts A, B, C, D and E, and the student really needed help with parts C, D and E. Now that means I don't really need to work through part A or B. Part A I'll probably leave because it's fairly straightforward, and I'd say most students can probably work through that and get their head around it. Part B, again, very mechanical. You know, if you kind of have solved one root of unity question, then you've kind of solved them all and you'd be able to work your way through this. What I've done in advance is I've done the work to effectively fill out this table, because filling out this table is what then lets you have the light bulb moments, I guess, to then answer questions C, D, and I guess E as well. So part B asks us for varying values of n. So we've got n equals 3, 4, 6, 8, 10, 12, and 20. We first have to find what the roots would be of z to the n equals 1 and work out their angles from the centi and radians. Work out the exact area of the polygon that would result from all those points in the Argand plane, and then calculate the area of that polygon divided by the area of a unit circle, which at first glance seems like a very odd thing to be asked to do, but we'll see that actually that's what helps us for part D. Part C then says deduce from that table an expression for the area of the n-sided polygon, which is that interesting proof that I mentioned at the beginning. Then part D says hence deduce the limiting value of the area of that polygon. So as n goes to infinity, what would the area of an n-sided polygon tend towards? And then part E says using information gained from our table, draw without the use of technology the roots of z to the 6 equals 1 plus I. So slightly different to what we're used to. We're used to z to the 6 equals 1, or z to the anything equals 1. But to have 1 plus I will require a bit of thought. And then finally, we need to state all the solutions of z to the 6 equals 1 plus I in that classic form acisθ. So as I mentioned, for part B, rather than you watch me work through all the mechanics of solving a roots of unity problem for all these different values of n, I've just prepared it in advance so that I can make reference to it for the other parts of these questions. So what we see here is for n equals 3, and I've basically just laid out the mechanics that you'd work through. You let 3 theta equal 2 pi k, because we know where k is an integer. For every multiple of 2 pi, that's when cis would be 1. Then you let theta equal 2 pi k on 3, and you've got theta between negative pi and pi, where the equality is on pi. So then you just rearrange for k. K has to be an integer, so you count all the integers between this range. You then use those values of k to work out theta. You use those values of theta to work out the angles that then plot in the Argand diagram. So these blue points here are the results, the roots of z to the 3 equals 1. I've then used a red pen to draw the polygon that results. And the technique I've used to then find the area of that polygon is to take half of one of these triangles, a half that effectively turns into a right angled triangle, and then I know that the angle, when I split this triangle in two, then the angle of that triangle must be half of the theta that I'm dealing with. So if all of these angles are 2 pi on theta's worth of movement, then half of it would be 1 pi on theta. So that's how I get to this 1 pi on theta. I know it's a unit circle, so I know in this case for this triangle, which I've replicated here, the hypotenuse is 1. So I know this angle, I know the hypotenuse. I can then say that cos pi on theta would be the adjacent over the hypotenuse. So cos pi on theta would be y on 1. And sine pi on theta, being the opposite on the hypotenuse, would be x on 1. So I can say that the area of this half of the triangle would be half times base times height, half times base, cos pi on 3, times height, sine pi on 3. And I leave it in that form. And then I say the area of this whole polygon, well, there's 3 triangles that are made. I've worked out the area of half of one of these triangles. So to get the area of one triangle, I double it. So 2 times this area. The 2 and the half cancel, so that you end up just with 3 cos pi on 3 sine pi on 3. And I've left it in that format. I haven't plugged it into my calculator because we'll see it's useful for part C to keep it in this format. Then the last part of filling out the table is to take that area and divide it by the area of a unit circle. The area of a unit circle is just pi r squared, but r is equal to 1. So it's pi times 1 squared, or just pi. So you're effectively plugging this into your calculator, dividing it by pi, or you could use divided by 22 on 7 as an approximation. We're only asked to give it to 2 decimal places, so that approximation will be fine. And so here we get that result being 0.41 to 2 decimal places. So that's kind of the mechanics of it. So then we do the same thing for n is equal to 4. We get a 4-sided polygon or a square. Do the same thing. Pick one of the resulting triangles, divide it by 2. Use half of the theta angle. Work out the area of that half triangle, double it, and then multiply it by the number of triangles, and you get, in this case, 4 cos pi on 4 sine pi on 4. And then do the math again. This time we get 0.64 to 2 decimal places. Then we do it for n is equal to 6. We end up with the area of the polygon being 6 cos pi on 6 sine pi on 6. And then this result being 0.83. Do it for n equals 8, same thing. We get 8 cos pi on 8 sine pi on 8. Hopefully you're noticing a pattern here. And then this result gets to 0.9. Do it again for n equals 10. So you see why I haven't made you watch me work through this. Same technique every time. So it's not a real high value add to just watch me do it. I'd encourage you to work through it, because getting all that practice definitely can't hurt. But for the purpose of this video, I can kind of skip over it. It's important that I've done it because I need to be able to point to it, but no need to go through it in detail. So here, when n is 10, the area of the polygon is 10 cos pi on 10 sine pi on 10. This result is 0.94. Hopefully you're noticing a pattern here as well. N is equal to 12. 12 cos pi on 12 sine pi on 12, 0.95. And then the last one we had to do was n is equal to 20. And you have a look, just when you split the 20 results around the unit circle, and you kind of start joining it to make a polygon, I mean, you're getting closer and closer to actually just replicating that circle, which is something worth thinking about when we get to the later parts of the question. But working through the same mechanics, we end up area of the whole polygon is 20 cos pi on 20 sine pi on 20, and this final result we get to 0.98 to 2 decimal places. So all of that is part B. That's all the work you would have to do to fill out that table in part B. So definitely a lot of work, but actually for every instance it's the same set of steps that you're following. So not a lot of, I guess, brain power required. It's really just grit. You have to just grit your teeth and work through it all. So now we get on to the next part, the part that the student was struggling, part C. And that asked us to get the area, or get a formula, I guess, for the area of an n-sided polygon. And that might sound like a kind of random question, I guess. It's like, well, where does that come from? We've been doing roots of unity in the Argand plane. How can I then get the formula for the area of an n-sided polygon? But hopefully you've noticed in each case we've been working out that area, and every time it was n times cos pi on n times sine pi on n, and that happened every single time regardless of what n was. So noticing that pattern, and I guess this is partly why the question writer made us do it for so many values of n, it was to convince us that when we get to this part C, we can with confidence say the area is n cos pi on n sine pi on n. And that's quite a neat result, to think that using complex numbers and roots of unity, you can suddenly get a neat formula for the area of any polygon, no matter how many sides it's got. And you end up with cos and sine in the result, and that's going to work for a triangle, a square, a pentagon, a hexagon, an octagon. You know, it's quite not something you'd probably come up with yourself, yet having worked through all this kind of preliminary effort, you can kind of see it's as clear as day that is the pattern. So that's part C. Part C is very easy. It just kind of drops out from all the effort of part B. And part D is quite similar. Part D says, I'll just double check, it says, deduce the limiting value of the area of the polygon. So basically, what's the limiting value of the area of this n-sided polygon? Or in other words, as n goes to infinity, what would this area go to? And you can't really just insert infinity here. You kind of might struggle a bit to then, you might be tempted to say, well, it's infinity times something, so it's infinity, but that isn't the answer. And that's where the question writer asking us to do this calculation becomes relevant, because if I flick through and just show you the pattern that we saw all the way back from n is equal to 3, we start at 0.41. Then as n gets bigger, 0.64, 0.83, 0.9, 0.94, 0.95, 0.98, and hopefully you see the pattern. As n gets bigger and bigger, we get closer and closer to 1. So what we can say here is that the limit, as n goes to infinity, as n continues to get bigger and bigger, of the area of the polygon, this n-sided polygon, divided by the area of the unit circle, that is equal to 1. I'll just do my divide sign here. So we can say with some confidence, having seen the pattern, that this limit goes to 1. So now what we can do is say, well, therefore, this area of the unit circle has nothing to do with n. It's always just going to be pi r squared, or pi times 1 squared, or pi. So we can kind of just move it up here and conclude that the limit as n goes to infinity of the area of the polygon is equal to pi, or pi times 1 squared, which is just pi times 1, or pi. So that's part D. Again, very simple once you've done all the hard work in part B. And that's why, I guess in hindsight, they got us to do part B. I mean, it seems like a lot of mundane effort. Maybe getting us to do it for so many values of n might have been overkill, but I guess doing it for that many, particularly for this part, lets you see things get closer and closer to 1, and it lets you kind of hopefully notice the pattern. So that brings us to part E, which itself has 2 parts. So part E, part 1, asked us to get solutions for z to the 6 equals 1 plus I. And this is a little different because so far we've been thinking about z to the n equals 1, so classic roots of unity. So you throw this plus I in and things start to change a little. But hopefully, and again maybe this is what part B was about, you do enough of these plots in the Argand plane and hopefully you can see that essentially if you were to add I to any of these points, if you just take any point and add I, maybe I'll come back to n is equal to 3 just so we don't have a very cluttered diagram. Or maybe I'll go to n is equal to 6 since we're dealing with z to the 6. If I have a point at 1, that's effectively 1 plus 0i. There's no imaginary part to this. If I then add I, I'm at 1, 1. I've effectively shifted up 1 in the imaginary plane. If I'm down here and I add I, I'm shifting up 1. Here, shifting up 1. Here, shifting up 1. This would just be negative 1, 1. And so, whilst it might look a bit different, all we're really doing is we're taking this diagram and in the Argand plane shifting it up by 1. And so the question asks us to do it by hand in the Argand diagram. So all we need to do, I'll just get my ruler, is effectively, I'll just, probably don't need much negative space. So if this is my real, this is my imaginary, this is the origin, I'll call this negative 1, I'll call this positive 1, I'll call this 1, and I'll call this 2. What we had for z or n, sorry, equals 6, where's that? Here, this diagram, we're essentially drawing it, but shifting it all up. So I'll just kind of get the unit circle going. Not the best circle, but hopefully you get the idea. And in terms of the points on the unit circle, we'll have one here, and we will have one about here, and we will have one about here, we will have one here, we will then get the 2 conjugates, and that's our 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, yes. So we're gonna essentially get this. I'll kind of connect everything. Now we're cutting through the point 1 here. And again, I haven't drawn this very well, but they should cut through the 1. So there are our points, and that's pretty much this part done. I mean, the question, I'll just read the exact wording, said, draw without the use of technology the roots of z to the 6 equals 1 plus I. These are those roots. That's it. We're in the Argand diagram, they're the roots. So that is that question done. So now we're on to E part 2, which is to write those roots. So what are the solutions to z to the 6 equals 1 plus I in the format acisθ? And so what we're really looking at is A is going to be the magnitude of the line from the origin. So for the first solution, it'll be that line. Second solution, it will be this line. Third solution, it will be this line. Then it will be this line. Then it will be this line. And then it will be this line. So we need to work out the magnitude of each of these, and hopefully you notice the symmetry of this diagram, notwithstanding I haven't drawn it very nicely. But if I know the magnitude of this, this and this, I've also got the magnitude of these, because whilst their direction is going into the negative part of the real axis, the actual magnitude is the same. So you really only need to find 3 magnitudes and then you've got all 6. But the other thing we need to do is to find these angles with the real plane. So that's where the effort's going to be. But again, the way these work, these are all kind of equally spaced. If I drew it perfectly to scale, they'd all be equally spaced around the unit circle. So once you've kind of got the first argument and the second argument, once you get the difference between them, you know the difference between all the arguments will be the same. So you can easily kind of hop around and work out what is the total angle from the horizontal plane. So now we just got to kind of work through. I'm just going to define the solutions. There'll be 6, obviously, always 6, always like to the power of n. And I'm just going to call them Z1, Z2, Z3, Z4, Z5, and Z6. So our challenge now is to write all of these solutions in this format. What's the magnitude and what's the argument? So I'll have to turn over, but for the first one, I think we're going to need trigonometry here, but this triangle here, I think is going to help us. Because I know this angle, and I know the length of this line, it's 1 because we're sitting on a unit circle. And I know this line too, it's also 1 because we're kind of on this unit circle and this is the new origin. It's basically going up 1. So with 2 sides and an angle, I think that's going to be enough for me to get the length of this side, the argument, A. And this angle here I can find probably by first finding this angle and then noting that it's in total 90. So I'll just turn over to start that. So we're looking at Z1 and I'll just draw up. So we'll go solution 1. And I'm just going to draw up this triangle that I think is going to help us. So we've got, it's kind of like this. And we know the length of this line is 1 and this line is 1. And if we go back to our n is equal to 6, here we are, the angle here was 2 pi on 6 was how far each solution moved. So here we're dealing with half of one of those, so we're at pi on 6. So this angle here will be pi on 6 because I've cut this whole triangle in 2, so this angle is effectively cut in 2, notwithstanding my poor drawing that's not to scale. So I know there's 2 sides, I know this angle. This I'll call A1, being A of the first solution. And if I draw a kind of this horizontal line that kind of represents the real axis, this would be theta 1, this angle here. So that's what I want to find, and I'll call this angle alpha, because if I can find alpha, then theta 1 will be 90 minus alpha. Alright, so what can we do? I think we can use the cosine rule. We can apply the cosine rule to work out A1, because using that rule we can say that A1 squared will be equal to the sum of these sides squared, so 1 squared plus 1 squared minus 2 times 1 times 1, 2 times the length of each side, times cos of this angle, pi on 6. So that's going to be equal to 1 plus 1 is 2, minus 2 times 1 is still 2. And cos pi on 6, hopefully you recognize that one. So if I did 180 divided by 6, we're at 30. So that's going to give us root 3 on 2. And if you just want to check that, we can say the cos, so we get this 0.866 and so on. If I did root 3 and divided by 2, we get the same thing. But hopefully this is one of those common angles that you commit to memory. So you get root 3 on 2. These 2's cancel. So a1 squared is equal to 2 minus root 3. So a1, the magnitude of it, is just going to be the positive square root of 2 minus root 3. So that's our a1. Happy days. Now to get our alpha, I think we can use the sine rule. So if we make use of our sine rule here, we could say that sine of alpha on 1 is equal to the sine of pi on 6 divided by a1. And we can put in our a1 as root 2 minus root 3. And therefore alpha will be the inverse sine of all of this on root 2 minus root 3. And at this point, I wouldn't be inclined to try and work this out. At this point, would just be getting out my calculator. So we go 180 divided by 6. The sine of that, half, that's nice. So, okay, this is a half. I'll just keep that in mind. So really, it's 1 on 2 times this. So if I did the square, if I did 2 minus the square root of 3, took the square root of that, times that by 2, because I've got my half on the top. Invert, take 1 over that, and then do the inverse sine of that, 75 degrees, okay? And that, in terms of radians, would be 5 pi on 12, which we can check. If I did 5 times 180 divided by 12, very good, 75. So that's our alpha, but we want theta 1. So we can say theta 1 is equal to this whole 90 degrees, so pi on 2, minus 5 pi on 12, minus our alpha. So that's going to be equal to 6 pi on 12 minus 5 pi on 12. 6 minus 5 is 1. So this is going to be just pi on 12. So therefore, we can say that Z1, our first solution, is equal to root 2 minus root 3 cis pi on 12. And remembering that that's the format that we've been asked to state all of our solutions. So we've done one of them. A cis theta is root 2 minus root 3 cis pi on 12. Alright, so that's Z1, 1 down, 5 to go. So I might have to turn over at this point. So now we're looking at solution 2. And if I come back to our diagram, so we're now at this solution, and I think this whole triangle is the one that can help us here. So I'll just redraw that. So we've got a triangle that basically looks like this. So that's 90 degrees. And it's a unit circle, so this is of length 1, this is of length 1, that's 90 degrees, happily. I'll call this A2. That's the length that we're concerned with. I'll draw a horizontal here. And this is theta 2. That's the argument we're concerned with. And again, I'll call this alpha, because if I can find alpha using similar technique to what we did with solution 1, I can then get theta 2. So again, I think cosine rule is going to help us. Oh, actually, no, Pythagoras. We can just use Pythagoras. Totally easy. A2 squared is equal to 1 squared plus 1 squared, which equals 2. So A2 in this case will be the positive square root of that, root 2. Simple. Okay, so now we've got our argument, our magnitude, our length. So now we'll get alpha to then let us get theta 2. So here I think the sine rule again will help. So sine of alpha on 1 will equal sine of 90 degrees, or pi on 2, divided by root 2. So alpha is equal to the inverse sine of sine pi on 2 on root 2. And I'm just going to use my calculator here just to save a bit of brain power. So 90 degrees, sine is 1, should have known that. So 1 divided by the square root of 2. Inverse sine will get us 45 degrees. And in radians, that will be pi on 4. And I'll just check that. 180 divided by 4, 45. Perfect. Okay, so if that's alpha, then theta 2 equals pi on 2 minus pi on 4, which equals 2 pi on 2 minus pi on, 2 pi on 4 minus pi on 4. 2 minus 1 is 1, so that's just pi on 4. So now we can say that Z2, writing that in the format we need, is the square root of 2 cis pi on 4. Alright, so that's solution 2. 2 down, 4 to go. If I turn over for solution 3, again, if I come back to this diagram, so we're at this point now, and it's really this triangle. And again, I've got two sides that I know the length is 1 because we're on the unit circle. So I'll just draw that. So this time the triangle looks something like this. We connect here. These lengths are both 1. Again, I want this total length, which is A3, and this argument I'll call theta 3. And the other thing I can say is that this is 90, so this whole angle will be 90 plus essentially the argument of our Z6, original kind of Z6, that angle there, which would be the, if I come back to our Z6, this angle here, 2 pi on 6, would be our angle here. I think that's right. Yeah, 2 pi on 6, or pi on 3. So I can say that this angle is equal to pi on 2 plus 2 pi on 6. So that's going to be equal to 3 pi on 6 plus 2 pi on 6. So that's going to be 5 pi on 6. And I think that's going to be useful for finding this length. Actually, one thing, before I go about finding the length, what we can say about this theta 3, this argument up to here, I can actually say is the movement from point 2 to point 3, that angle, is going to be the same as the movement from point 1 to point 2. So I can actually say that, well, first of all, let's find that movement. So what is theta 2 minus theta 1? What was that kind of angular movement between the 2 points? So theta 2 was pi on 4, and theta 1 was pi on 12. So that's going to give us 3 pi on 12 minus pi on 12. So that's 2 pi on 12. And I'm just going to leave it like that instead of simplifying it to pi on 6, because I think having it on 12 is just going to come in handy as we constantly add that. So I can actually say theta 3 is simply going to be theta 2, that angle we started with, plus 2 pi on 12. So that's going to be equal to theta 2, which is pi on 4, plus 2 pi on 12. So that's going to be 3 pi on 12 plus 2 pi on 12. So that's going to be 5 pi on 12 is our argument for this. So that was a bit quicker now. I don't need to keep finding this alpha and doing 90 minus. I'd get the same answer anyway, but now I can just keep incrementing by this 2 pi on 12. So that saves a little bit of time. But A3 we still need to calculate, and I think we can use our cosine rule here. So we can say A3 squared is going to be 1 squared plus 1 squared minus 2 times 1 times 1 times cos 5 pi on 6. So that's going to be 2 minus 2, and cos 5 pi on 6, if I do 5 times 180 divided by 6 and take the cos of that, minus root 3 on 2. So that's times minus root 3 on 2, cancel the 2's. So this becomes 2 plus root 3, which makes sense, it's clearly a longer line than the other two. So A3 is equal to the square root, the positive square root of 2 plus root 3. And notice the similarity with A1, which was 2 minus root 3. And when you look at the diagram, clearly A1 is shorter than A3. So that's kind of a nice sense check. But now we've got what we need. So therefore we can say Z3 is equal to root 2 plus root 3. Cis 5 pi on 12. And as I mentioned before, now that we've got our first three lengths, we know these three. And now that I've got my movement in arguments, I can work out these next three arguments very simply. So I think all the hard work has been done. So now we can just wrap up. We can say solution 4. And solution 4, we can say, let's start with A. So A4, just to make sure I get this right. A4, the length will be the same as A3. It's the same magnitude, it's just a different direction. So A3 we just worked out, root 2 plus root 3. So root 2 plus root 3. Theta 4 will be equal to theta 3 plus our increment, which we worked out was 2 pi on 12. Which will be 5 pi on 12 plus 2 pi on 12, which equals 7 pi on 12. So therefore our Z4 is equal to root 2 plus root 3, cis 7 pi on 12. Solution 5. A5 is equal to This line here will be the same length as that one, so that's solution 2. Solution 2 is root 2. And theta 5 equals theta 4 plus 2 pi on 12, which equals 7 pi on 12 plus 2 pi on 12 equals 9 pi on 12. Therefore, Z5 is equal to root 2 cis 9 pi on 12. And again, I'll just leave it in that format. You could divide top and bottom by 3. But technically it's still correct. I might just turn over for solution 6. The last one, very last part of this question. A6 will be, just to make sure I don't get this wrong, it's the same as A1, we can see. And that was root 2 minus root 3. So the square root of 2 minus root 3. And then theta 6 equals theta 5 plus 2 pi on 12, which equals 9 pi on 12 plus 2 pi on 12, which equals 11 pi on 12. Which again makes sense because we get very close to going all the way around, but not all the way. So 11 pi on 12 visually just looks about right. So that means we can say Z6 is equal to root 2 minus root 3 cis 11 pi on 12. And that is the end of that question. So a lot of work in that question actually. I mean, you may remember I didn't even do part A, I just skipped over it. And then part B I did in advance. So, you know, it's been quite a long process just to do the bits I've done in this video, but on top of that there's all the time that would have been taken to do part B. So very involved question, but again I think very interesting because particularly when we get to part C, this result is actually a valuable thing to know. You could take this result and commit it to memory and you might find it proves to be helpful. And to know that as the sides of a polygon get the number of sides gets bigger and bigger, you're just kind of getting closer and closer to a circle effectively, or the unit circle anyway, in terms of your area. And then, yeah, part E was kind of a little bit different. It took us on a bit of a different tangent, but yeah, got us to do something that at first might seem tricky. But when you realize you're just shifting up, you can then use trigonometry to get these solutions. So, and the symmetry meant you're really only doing 3 of them and then the other 3 fall out. So hopefully you've been able to follow along with all of that. There's quite a lot to it, but again, I think just when you break it down bit by bit, it's all definitely feasible, it's doable. I'm using just the basic principles of roots of unity and then our kind of classic trigonometry results. We're able to do everything we need to do. So yeah, hopefully if you were kind of daunted by that question when you first saw it, hopefully after working through this you kind of see that it's all within your grasp, it's all doable. You just need to methodically apply what you've learned and you will get there. So yeah, hopefully you found that helpful, and tick boom.